these lectures. I got a playlist up in YouTube. I need to talk with Mark over in the science department, our IT go-to guy, and see how do I get YouTube linked to Moodle, or cut and paste the link into
You
it.
could put the app with the link and we can go to it.
Yeah. If you send me emails, I do get them in Outlook. I thought I would see them in Moodle. Apparently I don't. All I see in Moodle are the emails I sent you. But I see your emails to me in Outlook, which is fine.
I think it's because we don't log into Moodle to message you.
How do you message me?
I just use my email. I don't know how you guys
Okay,
do,
okay. So
but I
that's
just use
fine.
Outlook, but
That's fine. That's fine. I think, yeah, that's okay. All right, well, here, let's just take a look at it. This is what I had for this DP. So I wanted you to move on in to problem 2 with that. So if you basically have that, and I kind of glanced at yours, then look at each one of yours clearly enough to see if that's what you have. Any discrepancy with that? Matter of fact, I'll give you that. Let me give you that.
Sweet. Looks good. Very difficult.
Okay, now that I got 2 things here. Okay. So, yeah, all we're doing is the partial p with respect to v at constant t. So you take that whole thing and do that. Constant t. All right, that's so that's a constant RT over, so it's minus v minus b to the second power. That's where that's going to go. Yeah, and this becomes a minus 2 times a minus, so a plus 2a to v cubed. Yes? And then this one is constant p with respect to t at constant volume, and so that's all a constant, so there's no change here. That goes to 0. dt to dt is 1, so this is just r over v minus b. All right, so now the second part of that question, and I'm not gonna belabor this or emphasize it too much. The main point here is there are some exact differentials and there are differentials that aren't going to be exact. And the other sub-point to that is that state functions, which are path independent, will generally, when you do the total differential of a state function, it should be an exact differential. All right, so what is the basic criteria? One criteria is that if you that it shouldn't matter what order in which you differentiate, you should get the same answer. So well, yeah, let me just say that.
What do you mean by which order?
Well, here's an example here. So up above there, we've got this partial p with respect to v at constant t is this, and up there we've got the partial p with respect to t at constant volume is that. So now, and that's as far as I expected you to go today. Did some of you try to prove it was an exact or not differential on it? Okay. So I'll leave this with you, but I'll kind of get you pushed offshore in this direction. So now, let's do this in the opposite order. And in other words, instead of, we know what this is right now. This is that. So now differentiate this with respect to t at constant v. So go ahead and differentiate that thing at with respect to temperature at constant volume, and then differentiate this thing with respect to volume at constant temperature. Differentiate that thing with respect to volume at constant temperature. And what you should find is that those will give you the same answer. Okay? You'll get to the same answer. So I'm going to steer you in the right direction here. In other words, differentiate that. I'll go down further, but there's the answer.
Wait, so...
So you want to, so what I'm doing here, I'm saying let m equal this thing. Let m equal this thing. So now differentiate m with respect to temperature at constant volume. And what is m? M is, that's what m is. So put that whole expression in there, differentiate it with respect to temperature at constant volume. So that's going to go to 0. Yeah, that's what you would do. You're going to differentiate this with respect to temperature at constant volume. So that's all going to be a constant. There's no change with respect to volume, or with respect to temperature going on here. So that goes to 0. And then just see what that would be. And you got your answer for what the partial of m with respect, let's see, what's the next thing down there? Yeah, I can go just a little bit further. So that's what we're doing. So we're saying m is this. M is this, which is that. So now put all of that in here and differentiate with respect to temperature at constant volume. Find out what that number is, what that expression is. N is going to be the other one. Differentiate it with respect to volume at constant temperature and see what that is. And what you should find is that the answer to this is the same as the answer to that, saying that it doesn't matter what order in which you differentiate this thing, you come to the same expression, which is one piece of evidence that this is an exact differential. Okay? So just go with that, and don't worry too much about this. We're going to get into today some things that are not exact differentials, like heat and work. It kind of begs the question, can you prove that heat and work? I'm not going to ask you to prove that. We're not going to go into differentiating those, and at least I don't think we will. All right? But that's enough. And you need that answer to factor into question 2 to carry on.
What's the significance of a differential being exact or not?
Well, state functions will give exact differentials. So this is basically a piece of a basis for saying, now we got a path independent property here, because it will lead to an exact differential. So it's independent of the way you got there. You should be able to differentiate it with respect to volume or temperature or any other parameter in there and get to the same place. Where if you do that with heat or work, you won't. You'll end up and say, I can't, I'm not getting the same answer. They're not reconciling. So that's the significance. And we're not going to take it much further than that. That's just about it. So 1B has you doing the DT, the total differential temperature. That one is a little bit more complicated. So just work with it best you can. And then, where's this homework? Well, I tell you what, we'll leave question 3 with chlorine, with those factors. Just do what you can to get those A's and B's back over into pascals or kilopascals or whatever. Do the best you can. The tables I went into, it seems the CRC table did have a way to convert it to other units, and I didn't pay real close attention to it. Okay, we'll segue on in here to chapter 2 in a second, but first a little relevant this day mechanical engineering. Okay, maybe a little PChem in there, I don't know. Woke up this morning, couldn't get out of my garage. Why? The torsion spring broke. I won't just address this to Grant, but why on a morning that's -7, -9 degrees would my garage torsion spring decide that would be a good night to break?
Materials get more brittle when they're colder.
Anybody know what I'm talking about, the torsion spring? Go home, look at your garage. There's a metal coil. If you think about the little spring that's in your ink pen, okay? Got a little spring in there? Not very strong. You can take it out and do da-da-da-da-da-da. Well, you got a very strong thing like that pulls your garage door up, and it's a metal bar that has been wound up into a spring like that, but it's about that big around, and it's wound about that long. How long it is stretched out, I don't know. Probably 40 feet long or something, but they wound it up, and then they torque it when they put it in there. And let's see, it's in its loose range when the garage door is up, and as the garage door is down, that bound is being bound up, so that then when you need to lift the garage door up, it actually is lifting the door up. But it broke. Second one of these, it broke on me. One broke down in Texas about 4 or 5 years ago. We thought a tree fell against the house. Because when it goes, it goes. They're powerful. And the metal just breaks. But go a little further, Grant. Yeah, it's more brittle. What else is happening to that band as the temperature goes down?
It's going to be shrinking.
Shrinking.
In theory.
So the metal is actually getting shorter, which would actually bind it up more. So my wife and I sit there for an hour and a half waiting for some guy to come. So I tried to lift the door up. I couldn't lift the door up with one of those broken. But he came, I said, was it the cold? And he said, well, it's cold and fatigue. He said, when they were within one or 200, only 100 or 200 cycles left in the spring, and it's cold, that's a pretty opportune time to fail. So bam. So it broke. Now I'll try to think about how to relate that to PChem, but I can't right now. But we are talking about materials, and PChem relates to everything. All right, chapter 2. Like I said, on a day like today, we're going to start talking about heat. We're going to talk about energy, internal energy, heat, work, and then enthalpy. So those are the 4 things we want to try to bring together in chapter 2. as we move on into chapter 2. We're not going to just kind of leave gases behind. Like I told you, gases are a simple way to start, but gases is matter in a particular phase. Thermodynamics is going to deal with matter in whatever phase it is in. And so these things are going to start coming together, liquids and solids and all of that. We're kind of talking about the material realm of things. So these are some terms I think I mentioned before, but let's just go through them. Extensive property depends upon the amount of the material. Intensive property, independent of the amount. And so actually these are two things we'll be getting into, I think, in this chapter. Specific heat of water is like 1 calorie per gram degree centigrade. Or specific heat is 1. It's independent of the amount. Doesn't matter how much water you have, that's its specific heat. Heat capacity is related to the amount. If I had a liter of water here at 50 degrees centigrade, and I had 10 liters of water here at 50 degrees centigrade, you could see that the amount of heat those two amounts of material would represent would be different. The heat capacity of the 10 liters of water, same temperature, but more water, there's more heat represented there. So we're not going to spend a lot of time on these, but the system, some well-defined portion of the universe. It's defined by its boundary surroundings, everything else in the universe. Open system can exchange material with the surroundings. So if we have a cup of water here at 90 degrees centigrade, it's got a certain heat in there, it's an open system. I've got a cup there. Water's evaporating. It's losing water. It's losing energy because of the water evaporating, the amount of energy it's carrying away with it. That's an open system. But if I had a closed container here with a certain amount of water in it and insulated and everything, well, just let's not say insulated, just a closed system, there's nothing, no material is going in or coming out of the system. Heat can still flow in and out of that closed system. So even though it's a closed system, doesn't mean that nothing can pass in and out of it. It's just, it can exchange energy, but not matter. So if we have it closed and insulated, we are perfectly insulated, and we're even stopping any flow of energy in and out of it. Pressure, force per unit area. The SI units. What the problem I ran into with this PowerPoint is it wouldn't let me use a lowercase letter. Everything was capitals. You can see here. Tried everything I could to get a lowercase a in there. I don't know why. And then when I copied and pasted it into Word and said, okay, no, in Word I think it'll let me do it. Then I copied and pasted it back into here, and it capitalized everything. So, oh well. I should have been an IT. Should have had an IT minor, I guess, just to help me out with what I got to do. So the Pascal is newtons per meter squared. This is a force and meters, so that should be a lowercase m. Newtons per meter squared is another way of looking at the Pascal. All right, here's our conversion from a bar to pascals. 1 bar is roughly, roughly 1 atmosphere. In South Africa, it went into a gas station to get air in my tires, and the pressure gauge was in bars. Okay? So what do we use to here? Pounds per square inch. So I'm going to put 32, 34 pounds per square inch in this thing. I go in there, the guy behind me didn't know what was happening. He's going to put 8 or 10 bars in his tires, and I thought, oh man, we're going to hear a loud noise here pretty soon. He doesn't realize every bar is 15 pounds per square inch. All right, so yeah, in some other countries, the actual pressure gauges at the gas station are in bars. So you're going to put 2.5 bars maybe in your tire, unless you got these little thin tires that go up to 60 pounds. Let me see, there was hit the wrong thing. Pressure. Okay, the Newton. 1 Newton equals 1 kilogram per meter per 1 kilogram meter per second squared. A force that produces an acceleration of 1 meter per second squared when applied to 1 kilogram mass is defined as 1 Newton. In SI units only, pressure would always be given in newtons per meter squared or pascals. So other common properties in the SI units: volume, meters cubed, kilograms, density, kilograms per meters cubed, pascals, and molar mass, kilograms per mole. 1 liter equals 10 to the minus third meters cubed. All right, energy, capacity, the capacity to do work or the capacity to cause heat transfer. Units are joules or calories. All right, so joules or calories. Let me see if this is where this fits in. Okay, 1 joule. So heat, the quantity of energy which flows across the system or surroundings boundary due to a temperature gradient. Units are often joules or calories. I'll add some units there for a minute. I was trying to think of some little object I can bring in here. So, but you're gonna have to use your imagination. Imagine we got 2 steel bars here. We've got 2 steel bars, and let's say 1 bar is at room temperature, and so let's say it's 20 degrees centigrade, and 1 bar is 90 degrees centigrade. 2 metal bars, same metal, and I bring them together. I just bring this bar into direct contact with that bar. All right, this one's at 90 degrees centigrade, this one's at 20 degrees centigrade. What is eventually going to happen? They're going to become the same temperature. So and something between 20 and 90, right? It's not that this one's going to become 90 degrees centigrade. This one is going to rise in temperature, and this one's going to lower in temperature. There's a certain amount of heat associated with this bar at 90 degrees centigrade, and that heat is going to flow to here. It's not this thing that is necessarily cooling this down, it's this thing that is warming that up. And as it's warming it up, it is cooling down. It's heat, the heat capacity in here is moving there. And I only use that example. You're familiar with chemical equilibria. Chemicals coming into equilibrium. But all I want to say is here is one way of thinking about this is thermal thermal equilibrium. We're bringing two objects at two different temperatures together like this, and they're going to reach a equilibrium thermally. They're going to reach an equilibrium thermally. So heat is going to dissipate to where the two bars are going to end up at the same temperature. And the whole system is going to be at equilibrium. So that's heat. A little bit about heat.
But they wouldn't have the same energy, right? They just have the same temperature. Or would you
Well, if they were exactly the same
specific?
mass, if they were the
Okay.
same mass, exactly the same metal, and all that sort
Yeah,
of thing,
then it would be the same
then they would
energy, but
end up at the same energy.
okay.
Yeah. So the quantity of energy which flows across the system due to a temperature gradient. So you would actually have a temperature gradient there. Something hot, something colder, and you'd have a temperature gradient. So 1 joule is equal to a Pascal times meter cubed. Let's just, so a Pascal is, we said a minute ago, newtons per meter. So if I took a Pascal and multiplied it by meters cubed, I would get Newton meter times meters cubed is going to equal Newton meter, which is the joule. All right, so there's this kind of relating all of those things together a bit. Okay, so I mentioned heat. Let's just mention work for a minute. Heat, work. Any energy which flows across the system or surroundings boundary that can change the height of a mass in the surroundings. Work is also measured in joules. Yes?
I have a question. Is it pascals and newtons per meter squared?
I think so. Let me see here. Yes. Yeah. We need that.
Square that and, okay,
Yeah, we need that.
got it.
Thank you. Newtons per meter squared. Because pressure is a force per unit area, so we need meters squared. Yes, exactly. So our meters squared are crossed now with meters cubed to get us meters. Exactly. Thank you. All right, so work is measured in joules. As a matter of fact, you can get, well, we're going to look at some units for work here in a second. The nth law of thermodynamics. I was going to call this the Rioch law of thermodynamics. I decided I didn't want to make that stab. The relationship between heat and work is not intuitively obvious. There is a very important relationship between heat and work. We're going to get into that as we get into internal energy. But let's just, now here enters joule, not just the unit, but the person. James Prescott Joule, I forget the year, the book has it, 1700s I think, 1800s. He was a brewer. I don't know if he's German. He was a brewer, and I don't know how this goes together with the experiment he did, but apparently you could have water flowing over a water wheel, and it turns a gear, and it can do some work for you. It can do work for you. So he started looking at just curious what the year is. Where are you, Jewel? Yeah, 1818 to 1889, so much later, much more recently than I thought about. So in the mid-1800s. So I don't think I could draw this very well, but he had a container here with, with a paddle in it, and he had a set of gears. Can you see this?
Yep.
Set of gears and a weight here. You could put a weight on here, and it would pull this down, and it would turn that, which would turn this. And so he would be mixing the water as the weight is dropping. So the weight is doing work as it's dropping. The mixer is mixing the water, and the temperature of the water changed. So this was, when I said this nth law, the relationship between heat and work is not intuitively obvious. Joule is the one that starts connecting it. Hey, look, there's actually a connection between the work you're doing and temperature. Work can generate heat or a temperature. I mean, other people are looking at this, they're boring things out, and they're grinding away at things, and they're getting hot, and so they're realizing there does seem to be a relationship between how hard you're working, or how hard something is working, and temperature. But he started getting into this a little bit more clearly, and he's attributed with this phrase, the mechanical equivalent of heat. So here is the mechanical equivalent of heat. And so today, we can kind of replace that experiment. We could do that experiment and measure temperature here. Or we can take that same amount of water and put an electrical heating coil down in there and know exactly how many watts of energy we're pumping into that water and see how the temperature goes, and we could develop a relationship there. You actually say, okay, here's electrical heat, here's electrical energy, here's mechanical energy, here's temperature change. So you're starting to relate heat and work. Okay, now, and this is just as we're getting into the beginnings of chapter chapter 2, and you're going to see this is a key equation, that work, little w, is equal to the pressure times the change in volume. Pressure times the change in volume is an expression of the work. And a couple practical ways of seeing how is work and pressure and volume related. Think about, they're not very popular today, but they used to be. Maybe it's just when I was a kid. The little CO2 cartridge cars that you could build. You could build a little car, get a little CO2 cartridge and puncture it, and the car would go sailing down the hallway as the CO2 in the cartridge under pressure is being released, and what is it doing? It's doing work. One I haven't seen myself, I hope I never will, but some people described it to me as a gas pressure tank that actually fell over and the valve got knocked off of it in a laboratory. and it went shooting down through the middle of the lab and busted through the back wall. So an example of how pressure and now what's happening, those tanks of gas are about 1,500 psi. So if 15 pounds per square inch is 1 atmosphere, that's about 100 atmospheres. Those tanks are holding about 100 atmospheres of nitrogen or oxygen or helium, whatever's in the tank. So there's 100 atmospheres in there. It's going to be released into 1 atmosphere of pressure. So that 35, 40 liters of gas is going to become so many liters. And so the pressure times the change in volume is the amount of work that that cylinder can do. Can do a lot of work. So here's a good little equation to keep in mind. And you would get liters here, atmospheres here. So you're getting liter atmospheres, which seems like an odd unit, but it is an energy. Energy work is usually with an energy unit. Liter atmosphere is 101.32 joules. So there's 101 joules per liter atmosphere. All right, temperature. Now, temperature and energy, we can't just talk about them interchangeably. Temperature is not a form of energy. It's a property of matter. It's at a certain temperature. It's proportional to the kinetic energies of the particles making up the sample of matter. So we'll get into that a little more, but they're not synonyms. Temperature is just not another synonym for energy, but it is certainly it's proportional to it. So temperature goes up, there has been some flow of energy, some change in energy. Some energy has come into that system if the temperature has gone up. Okay, just a couple more terms. We'll probably use this one a lot more, adiabatic. So an insulated system, it's impassable. No heat crosses the system or surroundings boundary. A term that's not used very often, or you could see diabatic. This is adiabatic. So this is the opposite of this. This is a system where energy does cross the barrier, across the barrier. So an adiabatic system, a calorimeter, where you're building a system, creating a system where you're going to keep all the energy in. You don't want energy flowing in from the surroundings. You want to know what's happening energy-wise in the system you're studying. So that would be kind of an adiabatic situation. All right, we've talked about this state function, a thermodynamic property which depends only on the final and initial states. They're independent of the pathway. Not to be confused with an equation of state or phase or value. So these are state functions. Pressure, volume, temperature, moles are the state functions we've looked at so far. Internal energy be a state function. Heat and work are not state functions. So if you want some examples of what is, what isn't, heat and work are path-dependent properties, whereas internal energy is independent of path, independent of how it got there. second. I left this. I purposely left off this delta U. Okay. Yeah, and I don't know if I want to go much further than this. Okay, the first law, we've got the 0th law related to temperature. First law of thermodynamics. Total energy of the system remains constant. Just restated another way, the internal energy U of an isolated system is constant. So in any universe, any total system you're looking at, the change in internal energy is going to equal the change in the internal energy of the system plus the change in the internal energy of the surroundings. Those things have to equal 0. All right, and what's kind of interesting here is that we've got this state function, internal energy, but the change in the internal energy is equal to Q plus W, the heat plus the work. Yeah. Q plus W. So here's a state function. So Q is your heat and W the work. If there's a change in the internal energy, it's going to be the sum of those two things. We'll eventually do an example here with the burning of gasoline, but you could imagine burning gasoline a couple ways. You could just take a drum and put some gasoline in here and burn it. And basically what you get is a lot of heat and almost no work. Don't get any work out of it. It's just burning in a drum. And yeah, does it get hot? Yeah, it gets hot. It doesn't do much work. You could imagine that as that is burning, that it's pushing down on the earth a little bit. So there's a little bit of work, almost 0, but a little bit of work as it kind of generates a pressure down and up. But it's open here, so it's all just going up. Or you can burn it in an internal combustion engine. And you're burning gasoline in the internal combustion engine. It's producing heat and work. It's forcing the pistons up and down, and you're converting your same amount of energy, but it's broken up in more work than heat. Not a lot of work. Do you know what? The internal combustion engine, I think, gives you about 70% of the energy comes out as heat, and about 30% comes out as work. I've always been telling my students, you want to become a billionaire? Work on that. Move more of it into work and less of it into heat. If we're running down the road with radiators on the front of our cars, why? To cool the engine? Because all the heat that the gasoline is generating, well, capture that heat into work, move that heat into work, and it's all relating to this equation right here. Certain amount of energy there, but it can be manifest as either heat or work.
What are the units on Q again?
Calories or joules. So calories or joules.
Okay.
So Q, when you talk about anything on a food label, is a big C calorie. Which is equal to 1,000 little c calories. All right, this is a nutritional calorie, and this will be interesting as we go a little further into here and realize that where do they get these numbers? If you go into McDonald's and say, oh, this Big Mac is 600 calories. Yeah, they burn it. They take the Big Mac and they burn it in a bomb calorimeter. They actually burn it and see how much it raises the water in the bomb calorimeter, and they say, okay, here's what you can get. And that is also, there's thermodynamics in here, involved in here. Why can they put that on the label? So you're going to eat that and that's how much energy you can get from it? Yes, it's a state function. It does not matter whether it goes through the Krebs cycle and generates energy in your body or whether we take it and burn it. So there's an example of a state function and how this operates. I don't care how we get from that Big Mac down to nothing and all the energy that's represented there, either through digestion or burning it in a fire, doesn't matter. There's a certain, the initial energy and the final energy are all we need to know. It's all we need to know. We don't need to know how it got there.
When you burn it, are you producing like CO2? Is that, or?
Yeah, CO2 and water, and yeah, you'd be burning it, forming CO2 and water. Maybe a little bit of carbon, depends on how well you burn it. I don't know what your body, how well your body burns it. It gets some fiber, some stuff it can't digest in there too. So yeah, so that's where they get those calories, from this stuff, and that's how it does work. It's only recently here that the Food and Drug Administration shifted over, I don't even know what it is, but they shifted over to some other measurement that can be taken in lieu of bomb calorimeter data. So that every time you come up with a new sandwich or something, you don't have to send it off and have it burnt to report the calories. They have some other test, and I don't know what that is, but I think they have replaced it with something that's proportional to what you get out of a bomb calorimeter, so you don't have to do that. Okay, let's see. See if we have enough time to even delve into this. All right, consider an ideal gas in a piston chamber. I don't have the figure here. Where the initial volume is 2 liters, and initial pressure is 8 atmospheres. Assume that the piston is moving up, that the system is expanding to a final volume of 5.50 liters against a constant external pressure of 1.75 atmospheres. Assume constant temperature for the process. Figure 2.2. There's 2.3. Yeah, okay, so we have a piston. So our pressure here is 1.75 atmospheres, and the gas is expanding to finally 5.50 liters. So calculate the work for the process. All right, it's straightforward. Pressure, or wait, not pressure. Work equals negative P delta V. So our external pressure here is 1.75 atmospheres, and our delta V is 5.50 minus 2.00 liters.
So the 5.5 liters is the initial volume?
Is the final volume. Final volume is
Oh, we're
5.5.
expanding.
Yeah, we're expanding. So it is expanding. Yeah, if we were compressing, then we would get a negative number there. Delta V would be negative. So delta V is positive, so the answer is negative. And what is it? 1.75 times what? 3.5?
Negative 6.13.
And you can see this is where you get this liter atmospheres. Liter atmospheres, which then can be converted to joules.
So you can do negative work. That's just. Right.
Let's see, the system is doing work on the surroundings. It's expanding. Yeah, so the system is doing this work.
So work refers to the system.
Yeah, in this case.
Negative work would be it doing work, right? Yeah.
Yeah. Okay, and now calculate the final pressure of the gas. All right, it'd be nice to have this whole question right before us again. Oh, okay. See right here, we have here's our initial pressure. Here's our initial volume. Here is our final volume. So what expression are you familiar with that could solve that problem?
U1 V1 V2
Boiled.
Yeah, Boyle's law. Okay? So to keep that right here, so P, so we're to the final pressure. So this is part B, final pressure. P1 V1 equals P2 V2. We want to know P2. P1 V1 divided by V2. So that's pretty straightforward. P1 is 8 atmospheres. It's 2 liters. And V2 is what? 5.5 liters. What's the answer? 2.91 atmospheres. Okay, so its pressure goes down as it's expanding, and that's the work it's doing as it does that. All right. Okay. We want to. I didn't want to go much further than start thinking. You're thinking about heat, work, and now internal energy, and how they are going to relate to one another. Okay. So we got all 3 of these now. The delta U equals Q plus W. We need to get that in. We will be working with enthalpy more than internal energy. And the book explains a little bit why that is the case. Even though internal energy is the more fundamental property, enthalpy is the easier one to get a handle on. So we're going to be working with enthalpies. They're not equivalent to internal energy, but they're related to that. So be reading about it, wrapping your mind around it, and getting there. What are these four things? Internal energy, enthalpy, heat, work. Okay, and the other problem set. I still didn't do the last problem. I did all the problems except the last one for problem set 1B. So if you do the last one and hit a speed bump or see something wrong, just send me an email.
What do you want the units to be for number 3? The answers?
Whatever, well, what do I want them to be? I guess I would want them to go back to SI units, but I'll accept them either way since I gave you that one with bars.
If we solve it in bars and then just go back to Pascal's, is that?
Yeah, that's good. That's good. Units are not trivial, right?
Yeah.
They,
As long as you know where it's what.
I mean, we knew that in Gen Chem, but it's kind of like quadrupled here because they're all different kind of units. And it's going to keep doing that.